Computers rule our lives. In 1965, Gordon Moore observed that the number of transistors on a computer chip doubled every year.
But there's a problem. We're reaching physical limits of just how small transistors can be if they've gone from thousands of nanometers in the 70s to just a few nanometers today. Why? At just above 1 nanometer, transistors are only a few times larger than an atom and about 500 times smaller than a red blood cell. At this small scale, strange things begin to happen.
On this scale, quantum tunneling comes into play, whereby an electron can just pass straight through a physical barrier. Ordinary computers are built around devices called computer chips. These use transistors, which are like switches. We express our information in bits, a 1 or a 0 for if a current is allowed through or not. However, when electrons can merely tunnel through the transistor, our usual logical operations break down. By the middle of the next decade, we could hit a brick wall in transistor development, bringing our rapid computing advances to a grinding halt.
So several years ago, physicists realised that if quantum physics had gotten us into this mess, it could damn well get us out of it, and hence spawn the birth of quantum computing.
Rather than bits, quantum computers use qubits, which can be any quantum system with 2 energy states, such as the spin of an electron, spin up or spin down. But in the quantum world, things work a bit differently. Sure, I can have a signal that's either 0 or 1, but how about it being both at the same time? As long as it's unobserved, the qubit can be in a mixture of the 2 states. Only once you measure it will it collapse to one or the other. This phenomenon, known as superposition, means that a quantum computer could undertake millions of calculations simultaneously.
As if qubits weren't weird enough, they can also entangle. This connection makes each of them react to a change in another state instantaneously, no matter how far apart they are. This communication results in correlations between them, such that by measuring just one entangled qubit, you can immediately deduce properties of its partners. For n qubits, there are 2 to the n correlations, each encoding 1 bit of information. So, a quantum computer sets up some qubits, entangles them, and then measures the outcome, collapsing the superpositions to a sequence of 0s and 1s.
In 2015, Google and NASA found that the D-Wave quantum computer was 100 million times faster than your computer. In 2016, Google used just 9 qubits to accurately simulate a hydrogen molecule. But only a couple of weeks ago, on the 9th of January 2018, Intel demonstrated its latest superconducting test chip with 49 qubits. This is just 1 qubit short of the 50 qubit quantum supremacy limit, at which quantum computers become more powerful than any classical computer.
Why do we need faster computers? They'd just be used for video games and super quick Google searches, right?
How about saving lives?
I suppose.
Complex calculations are required for us to accurately predict the weather. An extra puff of wind in London today could dramatically affect whether it will rain in New York tomorrow. But no problem if you have a quantum computer. Put in the data and it will do all the calculations at once. This would allow increased notice of major storms like hurricanes, preventing great loss of life.
A quantum computer would also significantly cut down the cost and time of drug development by being able to map out trillions of molecular combinations and quickly identifying the ones that would most likely work.
Using quantum computers for machine learning, where computers are able to act and react without explicitly being programmed, could help us do many things faster and more efficiently, leading to things like driverless vehicles and other advanced forms of artificial intelligence.
They could also be used for GPS, dealing with satellite data, encryption, the list goes on.
However, quantum computing is still quite theoretical, and it's estimated we'll need over 1 million qubits to have something viable. But nevertheless, this is an area of research which is rapidly expanding. Computers are everywhere, and very soon they'll be running 1 million times faster. We are on the brink of a quantum leap in our capabilities as a human race, so keep your eyes wide open, blink, and you'll find yourself in a whole new world.